Hello and welcome. In this video, I'm going to be talking about the anatomy of a real program, giving you an example of something that uses both loops and decisions. I'll talk a bit later about scientific programming and how we can plot data. And then I'll kind of summarize, wrap things up, and just talk about how you can stay motivated and how to pursue programming as a kind of lifelong effort. And so let's start with this program. Earlier I showed you how we could use the math module to figure out what 2 to the 8th power is, the math.pow function. And in this example, we're going to be doing this the long way. So if, let's say, we wanted to make a program really from scratch that computes 2 to the 8th power, how would we do this? It might look like this. So we start out at the top here with some variable definitions. So if you remember, these are parallelograms because they're inputs. And we need some basic information. The base, of course, is one of our inputs. It's 2 to the 8th power. The exponent here is 8. We want our answer to take on some value at the end that is the correct one, whatever it turns out to be. But here we put a placeholder, solve. We call the variable solve, and it's equal to 1. And we also have a counter that we've set to 0. And the way this program works is it's going to check first that the counter is still less than the value of the exponent. And then it's going to execute a loop, perform some operations, and then repeat this decision here. And presumably the value of counter is going to change until at some point this condition will no longer be met, in which case it will take the false root here, print out the answer, the variable which we called solve, and then end the program. What's happening inside the loop? So as long as counter is less than my exponent, we're going to perform this operation here on the solve variable. So initially it was 1. What it's going to do then is multiply this base value with whatever value is solved. So in the first iteration, solve is going to be equal to 2. And then we'll move to this second operation here, which is going to increment the counter by 1, right? Counter equals counter plus 1. Counter was 0. So after this first operation, counter's value will change to 1. Here's just been cut off a bit. The second time through the loop, counter, it was 1, so it's still less than 8, still less than my exponent. So we'll go through the loop one more time. And now this time solve is equal to 2. So 2 times the base 2 is going to be 4. And now we redefine solve as 4. And we execute this counter increment again. And now it's 2 instead of 1. And now we go back to the beginning of the loop, check the condition again. Counter is 2. It's still less than my exponent. So we go through the loop again. And oops. Now solve is equal to 8. Counter goes up to 3. Back through the loop. Solve equals 16. Counter is 4. And so on. So we keep repeating this until at some point counter equals 8. And now when we go through the loop, we go back to the beginning. We no longer satisfy this condition. Counter is less than my exponent. So we go this way and print the answer. And if we remember, it's 256 here. So let's try implementing this in Python. We can start my base equals 2, my exponent equals 2, solve equals 2, counter equals 2. And you can see the flowchart really helps makes things simpler. We can do this with a for loop or a while loop. Let's try the while loop. So while counter less than my exponent. Oh, and sorry, this should be 8, 1, and 0. And we need a colon here. So as long as this condition is met, do what's in the loop. So what's in the loop? Well, we're redefining solve to be this product of the base and whatever solve is. Oops. And we're incrementing the counter. Remember, we can do that with counter equals counter plus 1, or we could just as well do counter plus equals 1. This will do the same thing. And then at the end, we want it to print. And we don't want to put the print in the loop, otherwise it will print out the answer every time. Maybe we want that, but if we're following the format of our flowchart here, we want to do this at the end. So print solve at the very end. And let's try this. 256, there's our answer. Let's say we wanted to do this as a for loop instead. Then we wouldn't even need this counter here. We can just say for I, or counter, we call it, in range 0 to my exponent. Colon. And we do something similar, but not exactly the same. So we do solve equals solve. And let's say if we tried to do this, solve times my base. No, wait, yeah, that should work actually. Yeah, and then it will just do this 8 times, right? Because we've created a range that has integers from 0 to my exponent. So that's just going to be 0, 1, 2, 3, 4, 5, 6, 7. So that will be 8 iterations. And even though this value counter is changing, we're not actually using it in the computation. Basically, this is just serving the function of creating a loop that happens 8 times. And that's the only thing. We don't actually need to use this counter variable for anything else. And then at the end, print solve. We do it right? Yes, 256. Okay. Yeah. For while loop and for loop. Yes, and then yeah, you can also use the math.pow function. In Python, you can also just use double asterisk here to create an exponent. So scientific programming involves a lot of plotting and utilizing data. And I think this can be one of the most useful things to learn as early as possible because yeah, a lot of programming at the basic level is a bit abstract. You know, when are you going to need to, you know, compute 2 to the 8th power? When are you going to need to know how to write an algorithm that computes 2 to the 8th power? Quite rarely, but plotting data is something that is quite useful. And we can do it right here in Google Colab using the import file syntax here. And let's fetch this my data file.txt. Unfortunately, you need to find your own data. But I can make this text file available to you on GitHub. And what we need to do now is figure out what's in this text file. And right now we've just uploaded the text, but we haven't stored it as a variable, a data variable yet. So that is what the next few lines of code are. And I'm just following from the slides here, but we'll go through it. So here we're importing our libraries. NumPy, of course, we're going to be using for doing these array operations working with data. And here we're calling our data file DLS. So this is in fact dynamic light scattering data from a device that analyzes particles in fluids. And NumPy has a handy function called gen from text, or gen from txt. And this will take as its input the name of a file. So we call this my data file.txt. And it turns out the file is delimited by commas. So commas are used to separate the data points. And we want this to be stored as floating point data. And if we were to Google this or search, actually, we could do help function np.gen from txt, and we can get some information on this. So if you're unsure, for instance, on what we need to put, what we need to feed this function for it to work, here we have it: file name, data type, delimiter, and we can just, these are called arguments. They're not, their order doesn't matter. So the first parameter that we add, we don't need to specify, using a word or an equal sign here. This is like a required data format. So if we wanted to run this function, we could do it just like this, and it would take default values. But if we're going to use something other than default values, we can specify these other arguments here, just additional inputs, basically. So we could go with the default delimiter. The default is in fact none. In this case, we have comma separated data. So we do want to use a delimiter. So that's why I've added this comma here. And the default data type is float. So actually we could, I think, remove this and it would still work. And if we check then what's in this file, DLS, we see it's a NumPy array, 2 columns and a bunch of rows. And if we remember our slicing or indexing rules for NumPy arrays, we can use this comma format for matrices. If we wanted to get, say, the 0th row and 0th column, should be this 0.4 here, we could do that with, oops, where'd it go? I'm just going to delete this cell here. We could do this with bracket and 0, 0. Let's say we wanted to get the entire, let's see, the 0th row and all columns. And we only have 2 columns, so it looks like that. What if we wanted to get all rows and the 0th column? So that should be all of these numbers here that are changing a lot. And sure enough, 0.4, 0.4632. So you can see it's this first column. What if we wanted to get the second column, column 1? And we would do it like that. So in this example here, we've said x is equal to column 0 and y is equal to column 1. And we'll use matplotlib's pyplot function, which just produces a line plot, very simple, to plot these data. And matplotlib, if we want to, we can also add some axis labels: particle diameter, nanometers. We can add a y label, frequency, and you can see here labels have appeared now. And so this is a really nice thing to be able to do. And I recommend, if you have some old data, to try to do this, an old Excel sheet, a spreadsheet. Give this a shot. Yeah, so here's a variation on this. Let's say we wanted to normalize this data. So here we added a line. I'll just copy it here. We'll change, do an operation on all the values in this y list here, y array here, which is the sum function. So I mentioned that NumPy has a lot of good functions like finding the average or the standard deviation. One of these is sum. So it takes as its input a list or an array, and it will generate the sum. And yeah, we can see what that is. Normalize. It's 99.9. And often if we have data, maybe if it's a distribution data, maybe we want the cumulative, the integrated area under the curve to add to 1, for instance. So we could divide this data then by this sum here so that everything sums to 1 instead. And we could do that using this block of code. We could use a for loop. So we could say from range 0 to the length of y. So this will just go through every item in y. We don't need to know how many items it is. We could count it, right? We could check, looks like, we could count every one and say from range 0 to 100 or whatever it is. But it's much easier to just use the length function here, and then we know that it's just going to go to the end of this vector here, to the end of this list. And we can use the row. Row is our iterate here for this for loop. And it's going to take on the values in this list, just integers, 0, 1, 2, 3, 4. And those integers can correspond to positions in this list. So we can use row as our index. So if we want to fetch, the 0th item, the first item, the second item in that order, we could just say y and index row here, and do some operation. We could set it equal to 1, and then, y normalize. Y would become just a bunch of 1s, right? But instead, what we'll do is set y equal to whatever it is currently divided by this sum that we computed earlier, 99.9, y normalize. And this should then normalize the array so that it sums to 1. And of course, I've made a mistake because I've redefined y as 1, so we need to re-import everything here. Okay. And the only thing that's going to change when I rerun this plot is the values on this y-axis here. The shape should be the same. But yeah, now the values have been divided. So that's an example of a realistic data plotting. This is real DLS data. And normalizing it is a really common thing. Using a for loop is a perfectly reasonable way to process a set of data like this. Yeah, here's another example. So matplotlib has all sorts of different functions. In the last example we used the plot function, but that's for making line plots. Matplotlib also has a scatter function. So really, it's good to just go online and Google different things you can do with matplotlib a lot of times. And you have a lot of options, ways to change the colors, customize these plots. This is really something to Google. And yeah, so this can be a bit tricky dealing with these arrays. And I realized this. And I think one thing that can be helpful is, most of us are really used to working with spreadsheets, and arrays in Python or in programming are really similar to columns and rows in spreadsheets. And when you do something like, in Excel, you have a spreadsheet, maybe you would create a column, say like values from 1, 2, 3 up to 28, and maybe you want to compute the square of those values. So you would make a column right next to it and create a formula that say like, take the cell to the left and take it to the second power, raise it to the second power. And then you would grab the handle and drag this down and you compute that. So that's really similar to what we're doing with a for loop, like in this normalization example. Basically, we have a, our column in this case is this y, is this variable y. It's a list, it's an array with a bunch of values in it. And it's not visual the way an Excel spreadsheet is, but it's the same thing. It's just a list of numbers. And the for loop is doing the same thing that we're doing when we drag this thing down. It's performing one operation, but multiple times on different inputs, changing inputs. And in this case, the inputs that are changing are these values on the left. In the case of the for loop, it's the values in the input to the for loop here, the iterate here that's changing according to those values. So this is my tip, I guess, for trying to visualize these things. This is pretty much the most important thing for scientific programming, is just being able to understand arrays and how to manipulate them and access them, and in your head kind of visualize them. And really you can do, this gets you very far being able to do this. Here's an example, like plotting this. Yeah. So quick quiz then. Let's say we have a 10 by 2 NumPy matrix, or a two-dimensional array of data points called myData, np.array, and here you can see it's made from these two lists here. The first subarray or column in the data represents an independent time variable, and the second represents a sensor reading variable. How could we obtain the first data point, i.e. the first pair of time and sensor values? So let's think about this. We want the first pair. Since this is a NumPy matrix, we can use this column format. And the way to interpret these numbers here is, if you remember the mnemonic Roman centurion, we're going to think about the rows first, Roman, and the columns, centurion, RC, in that order. So here, the index here, this is going to retrieve all rows and the 0th column. Okay, and then if we look at that, what we want is actually the first pair of time and sensor values. So we want we want all columns basically, and the first row, or the 0th row. So I believe it should be the second one, but just to be sure, let's try it out. And this will be a really common thing with these indexing things. Even myself, I often have to try them out to know what the correct one is. So there's really no shame in that. Let's just make a small one. Let's see. Like that. And we want the first pair. So we want 1, 0. So let's try it. Matrix, 0th row, all columns. Nope. Okay, I have it backwards then. So I think then what we want is all rows, 0th column. Could that be right? Yes. Okay. And yeah, this does make sense. If we print this out, what we want is all rows 0. Yeah, so yeah, the order here, I've mixed it up a bit. So this is the first row, second row, not first and second columns, as I've said here in the problem statement. So yeah, in fact, what we want is, yeah, we want all rows and the 0th column, 1 and 0 here. So that makes sense here. All rows, 0th column. Yeah, this can be really tricky. So yeah, feel free to Google this kind of thing, and maybe even better to just play around with it, try it out in your live environment. So that's about all the practical stuff that we'll go through. I'll just mention here some tips, some suggestions. Programming is really something that that you have to do it a lot and kind of commit to it, I think, for it to really change you. But when you do this, the difference is huge, and it can be a really good thing to have in your life, I think. And to help you with this, I think it's good to utilize all the resources we have. I mean, this is another a huge advantage with programming. I mean, there are not many things out there where you can basically get to a professional level through completely online resources. Everything is online. You know, this community it's completely open. It's not like that with rocket science, for instance. If you want to learn how to build rockets, then you know, you can't just you know, the theory can only take you so far. You know, at some point you need access to materials and supplies, and the budget gets prohibitive at some point. But with programming, there's really nothing limiting you from being as good as the best people in the world. The limit is your own motivation and imagination. So I recommend YouTube. This is really probably the easiest way to just get in right away. You know, start watching tutorials, everything from basics to specific libraries. So we'll be using BioPython in this course, but you know, it might be you have you know, a network problem that you're interested in, or a particular visualization that you want to make. There's bound to be tutorials on pretty much everything you can imagine. Uh, Online courses, of course, there Python especially. There's just a bunch of courses, and I'm not sure which ones are the best ones. So you might need to experiment around with them a bit. But Coursera and EDX and other platforms, I'm sure you'll be able to find lots of decent Python courses. And I recommend as scientists to focus on data or data visualization, data science, or scientific programming courses, because these are probably going to be more interesting. There are going to be a lot of courses out there that are focused more towards, say, web programming or game programming, different stuff. Forums, of course, is a huge resource. So whenever you Google, whenever you get stuck, you know, you Google something, usually the first thing that pops up is a Stack Overflow post. Someone has asked the same question as you and received 50 billion answers. And, you know, this is a resource that has really matured over time. So almost all the answers you can imagine are already out there, but you can also post your own. I've done this myself. And Reddit, there's large communities, Discord servers. It's a huge, vast community to get to know. And this is another tip: come up with your own projects. So something you care about. A really easy one is just take a spreadsheet and try converting it to Python. You probably have, some old data from a lab exercise that you did, 2 years ago, or some accounting calculations, your taxes or something like that. Like, just take an old spreadsheet and try doing whatever it was you did in the spreadsheet, but in the context of Python. And this can be a great exercise. Another thing, pick a learning goal. Pick something from a math or science textbook and try implementing it in Python. I think a great one for this is networks. So like, I have a big fat book on network mathematics, and I never really made much progress in this book until I tried just replicating some of the information in Python, and just doing it practically. And to me, it's much easier than actually reading through these dense texts. And of course, bioinformatics, machine learning as well. Another good project idea is, pick a boring or repetitive task that you have to do often. So I gave this example early on about, scripting for formatting pictures for my lab notebook, for instance. But could be something else. Maybe you have to copy and paste and rename a file 100 times or 1,000 times. This is a perfect thing for automation. And last, visual things. I think this is one of the most satisfying ways to program. When you produce something visual, it's really, you feel like you've made something, and I think it can be really nice to actually produce some kind of product. So try finding some old data, maybe, or creating an animation. Try to replicate a plot that you find online. I think these can be especially enjoyable. So programming, I think, it's not very hard to get into at a really basic level. And it's quite useful right away, I think, as a skill for just doing basic stuff, analyzing data, solving certain kinds of problems. But I think it can really be a discipline. You can pursue it, and at some point you reach a level where it becomes a creative form of expression, and you can do really interesting stuff that is kind of a manifestation of your own personality and your own style. And I think it's really nice to have something like that. It's similar to other arts or pursuits. At the very basic level, it's very technical. You're kind of learning how to take your first steps, but at some point you reach a point when you're not really thinking about these technical parts so much as the products that you're making. So that's all. I recommend taking a moment to pause to reflect on all the material that you've learned today. Try typing or writing down all the things that you can recall from the lecture, and this can help you solidify some of your knowledge. And with that, I'll end this video, and tomorrow we'll pick up with more intermediate programming and more complex programs, and building a bit on the material from today. Thank you.